So we learned in the last section in the course that Newton's laws of motion can give you the acceleration of an object. So let's assume you can solve a certain F equals ma problem. You solve for the object's acceleration. Who cares? What good does the acceleration do you? I mean, we learned in the section on describing motion that, like, theoretically, the acceleration tells you how the velocity is changing. But in practice, what can you really do with the acceleration of an object? It seems like a very not that useful thing to have when you get it, because it doesn't sort of directly tell you what the object is doing right now. Well, that's where this little section of the course comes in. If you're following along in the Knight, Jones, and Field textbook, I've skipped a bunch of things, which I'm now going to come back to, because I wanted to lay down the kind of fundamental physics first, and now go back to actually trying to describe the motion of objects with a known acceleration. So in this class, we're really only going to attempt to solve one particular case, which is consider the case of an object with constant acceleration. And when I say constant, I mean constant in both magnitude and direction. What does an object with constant acceleration look like? What is its motion like? That's the question we really want to answer in this section of the course. All right, so I'm going to kind of skip over a lot of the details here. You can find a lot of extra kind of mathematical details if you look at the lecture notes. Let me sort of jump to the final conclusion. The most fundamental thing we know about the acceleration is, in cases where the acceleration is constant, we know that the acceleration is equal to the average acceleration, because if something is constant, it equals its own average. And we know that the average acceleration is delta V over delta T. So one example of something that the acceleration tells you is, let me drop the vector symbols and assume that we're just looking at components here. We will have acceleration times time equals V final minus V initial. So this gives you an idea of one possible equation you could use. In this case, let's say that you know the initial velocity of an object and you know its acceleration, then you can determine the velocity at a later time. Now that is something that sounds useful, right? Now you can use the acceleration to find the velocity. In a similar spirit, but in a more convoluted way, you can write down a number of other equations which allow you to describe an object's motion when its acceleration is constant. Let me just flip over to the PowerPoint presentation rather than try to copy all these equations down by hand. So you can generate a total of 5 equations, the 5 that are shown here, which relate an object's, which relate an object's position to its velocity and its acceleration. And those are called kinematic equations for constant acceleration. So that is what is shown here, these 5 equations here. So what I want you to notice, first of all, when you kind of look at these equations, is first off, there are a total of 5 variables in these equations. And those variables are, we've got delta x. This is the displacement, which we learned about earlier in the course. Just remember, by the way, let me just remind you, displacement only depends on the initial and final state. It doesn't depend on the actual path taken by the object. So that is true for this delta x as well. This does not necessarily tell you the distance that was traveled. It just tells you the displacement. We have the initial velocity and the final velocity, which I use VO and VF. Some people use slightly different symbols. O stands for like t equals 0, and F stands for final. So these are the object's velocity at the beginning of a certain time interval and at the end of a certain time interval. And that is the same time interval over which we're taking the displacement there. We have the acceleration of the object. Notice these are all the quantities that I introduced at the beginning of the course. And by the way, just a reminder, the acceleration has to be constant for this process. So that's why for the acceleration, there's no like initial or final, because it has to be constant. So the initial acceleration equals the final acceleration automatically, or this doesn't work at all. And then lastly, t or delta t, this is the time elapsed during this time interval that we are examining. So those are the 5 variables that appear in these equations. And the other thing I want you to notice is that each of the equations only actually has 4 variables in it, but it's a different combination of 4 variables in every equation. So each one of these 5 equations here contains a different unique combination of 4 out of the 5 variables. And as you can see written here, the first equation has all the variables except delta x. Second equation has all the variables except VF. The third equation has all the variables except VO, and so on. So as a result, once you have access to these 5 equations, if I give you any 3 of the 5 kinematic variables, you can solve for the other 2, because the equations actually only have 4 variables in them. So as long as you know 3 out of the 4, you can solve for the 4th one that's left over. So using these equations seems very overwhelming and intimidating at first, because you have a whole bunch of equations thrown at you with a bunch of different variables in them. But they're actually not hard to use at all, as long as you have a very organized, systematic approach about how you're doing it, which I'll explain very step-by-step later. But the essence of it is that you want to identify what are the 3 variables that you know, and once you have the 3 that you know, then you say, what's the 4th one that I want to solve for? And then you choose an equation that involves the 3 variables you know, plus the 1 variable you want. You choose the equation that has that particular combination of 4 variables, and you solve for the one you don't know. And that's the essence of how you describe an object's motion using these kinematic equations, which we'll see a number of examples of increasing complexity as you go through the future videos.